Right now, as you're watching this video, you're surrounded by the oldest light in the universe. It's passing through you. It's filling every room you've ever been in. It's everywhere in the sky, day and night, and yet most people have absolutely no idea it exists. This isn't science fiction. This is real light, ancient beyond comprehension, that has been traveling through space for nearly 14 billion years. And by the end of this video, you're going to understand exactly what this light is, how we can detect it, and why it's one of the most important discoveries in the history of science. Now, this topic is vast and incredibly rich. There's so much to explore here that I've put together a detailed ebook that goes even deeper into the cosmic microwave background and the early universe. If you want to keep learning after this video, you can download it from the description below. It's a great resource if you want to dive further into the science we're about to cover. So let's begin with a question that might sound simple, but has profound implications. What does it even mean for light to be old? When we talk about old light, we're talking about something that most people never stop to consider. Light doesn't just appear instantly, it travels, and it travels at a specific speed, about 300,000 kilometers per second. That's fast. Unimaginably fast by human standards, but in the context of the universe, it means something extraordinary. It means that when you look at something far away, you're not seeing it as it is now. You're seeing it as it was when the light left it. Look at the sun. You're seeing it as it was 8 minutes ago, because that's how long it takes sunlight to reach Earth. Look at the nearest star beyond our solar system, and you're seeing light that's over 4 years old. Look at a distant galaxy, and you might be seeing light that left billions of years ago. The farther we look into space, the further back in time we see. But here's where it gets interesting. There's a limit, a boundary, a wall in time beyond which we cannot see, not because our telescopes aren't powerful enough, but because light itself couldn't travel freely back then. In the earliest moments of the universe, conditions were so extreme, so chaotic, so incredibly hot and dense, that light was trapped, it couldn't escape. The universe was opaque. So here's the mystery. If the early universe was this thick, glowing fog that blocked all light, how is it possible that we can see anything from that era today? How did any light survive? And more importantly, where is that light now? Let's go back, way back, to just after the Big Bang. In those first moments, the universe wasn't anything like what we see today. There were no stars, no galaxies, no planets, not even atoms as we know them. Instead, the universe was filled with an incredibly hot, dense plasma, a churning sea of particles, protons, electrons, and photons, all crashing into each other in a cosmic storm. Imagine trying to see through a thick fog, except this fog isn't made of water droplets. It's made of charged particles that are so tightly packed together that light can't travel more than a tiny fraction of a distance before it hits something and scatters in a new direction. Every photon that tried to move forward would immediately collide with an electron. Bounce off, change direction, collide again, over and over and over. Light couldn't escape. It was trapped, endlessly ricocheting inside this cosmic fog. This wasn't just true for a few seconds or a few minutes. This went on for 380,000 years. That's how long it took for the universe to cool down enough for something remarkable to happen. That something is called recombination. And it changed everything. As the universe expanded, it cooled. And eventually, it cooled enough that electrons, which had been zipping around freely, slowed down enough to be captured by protons. When an electron binds to a proton, you get a hydrogen atom. The simplest atom, the first atom, and once atoms formed, something incredible happened. The universe became transparent. Suddenly, for the first time in cosmic history, photons didn't have to keep bouncing off free electrons. They could travel. They could move freely through space in straight lines, uninterrupted in every direction. This moment, this transition from opaque to transparent, released a flood of light into the universe, and that light has been traveling ever since. This is the light we're talking about. The light that was released when the universe first became transparent. It has a name, the cosmic microwave background, or CMB for short. But don't let the technical name fool you. What we're really talking about is the very first light that ever traveled freely through space. It's the afterglow of the Big Bang, the oldest light that exists. When it was first released, this light was incredibly bright and hot. It filled the universe with a warm glow, like the inside of a star. But that was nearly 14 billion years ago. And in all that time, something happened to this light. The universe expanded, and as it expanded, the light stretched with it. Imagine a wave on a rubber sheet. If you stretch the sheet, the wave stretches too. Its wavelength gets longer. In the case of light, longer wavelengths mean lower energy, and lower energy means cooler temperatures. So the light that started out as visible light, glowing bright and hot, has been stretched over billions of years into microwaves. The same kind of radiation your microwave oven uses to heat food, but much, much weaker. Now here's the part that should blow your mind. This light didn't vanish. It didn't fade away into nothingness. It didn't get lost somewhere in the distant cosmos. It simply changed form, and it's still here right now, all around you, coming from every direction in space. You might be thinking, if this light is everywhere, why can't I see it? Why don't I notice it? The answer is simple. It's not in the visible part of the spectrum anymore. It's been stretched into microwaves. Your eyes can't detect microwaves, but that doesn't mean the light isn't there. Every direction you look, even in the darkest, emptiest part of the night sky, this ancient light is present. It's a faint glow, incredibly uniform, coming from every corner of the universe at once. In fact, if you've ever seen an old analog television, the kind with static when you tune it to an empty channel, you've actually seen a tiny bit of this ancient light. About 1% of that static, that random noise, is the cosmic microwave background. It's the universe's first light leaking into your living room. Of course, to really study this light, you need more than an old TV. You need incredibly sensitive instruments. Satellites like COBE, WMAP, and Planck have been launched specifically to map this radiation in exquisite detail. They measure the temperature of this light across the entire sky, looking for the tiniest variations, the smallest ripples in an otherwise smooth glow. And what they've found is nothing short of extraordinary. Because this light, this ancient relic from the universe's infancy, isn't just hiding in plain sight, it's telling us the story of everything. Think of the cosmic microwave background as a baby picture of the universe, not a picture of what it looks like now, but what it looked like 380,000 years after the Big Bang, when it was just a tiny fraction of its current age. But this isn't just any picture. It's encoded with information, incredible amounts of information. When scientists map the CMB, they don't see a perfectly uniform glow. They see tiny temperature variations. Some spots are slightly warmer, some are slightly cooler. These differences are minuscule, just a few millionths of a degree, but they're hugely important, because those tiny variations represent the seeds of everything we see in the universe today. The slightly denser regions, the warmer spots, are places where matter was beginning to clump together. Over billions of years, gravity pulled that matter into tighter and tighter concentrations, eventually forming the first stars, the first galaxies, and the massive cosmic web of structure we observe today. Without those ripples in the CMB, we wouldn't exist. The universe would be completely uniform, with no stars, no planets, no life. But the CMB tells us even more than that. By studying the precise pattern of these temperature variations, scientists can measure the age of the universe. They can determine its composition, how much normal matter it contains, how much dark matter, how much dark energy. They can calculate how fast the universe is expanding and whether that expansion is speeding up or slowing, like we have learned it is. They can even test whether space itself is curved or flat. All of this information, the entire story of the cosmos, is encoded in a faint glow spread across the sky. A glow that most people will never notice, but one that scientists have spent decades studying with instruments of extraordinary precision. So how do we actually observe something this faint, this old, and this important? It requires some of the most sophisticated technology ever built. Satellite missions like the Cosmic Background Explorer, or COBE, launched in 1989, were the first to measure the CMB in detail. COBE confirmed that the radiation had the exact spectrum predicted by Big Bang theory, and it detected the tiny temperature fluctuations that would later become the focus of intense study. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, which launched in 2001 and spent 9 years mapping the CMB with much greater precision. WMAP gave us our first truly detailed picture of the infant universe, and its data revolutionized cosmology. But the most detailed map we have comes from the Planck satellite, a European Space Agency mission that operated from 2009 to 2013. Planck measured temperature differences as small as 1 part in 100,000, creating a map so precise that it's become one of the most iconic images in all of science. These aren't the only tools we use, though. Ground-based telescopes in remote high-altitude locations observe the CMB from Earth, filtering out interference from our atmosphere. Balloon-borne detectors fly high above most of the atmosphere to get clearer views. All of these instruments work together to measure the same thing, the faint echo of the universe's birth, and when the data comes back, scientists convert it into maps. Beautiful, colorful maps that show the ripples in the early universe, the patterns that would eventually become everything we know. It's incredible when you think about it. We can detect something so old, so faint, and so far removed from everyday experience. And yet we can study it with such precision that it tells us the fundamental properties of reality itself. There's something deeply moving about the cosmic microwave background, something that goes beyond the science, beyond the data. This is the oldest light we will ever observe. Not just the oldest light we've found so far, but the oldest light that can possibly exist. There's nothing older to see, because before the CMB was released, the universe was opaque. Light couldn't travel. This is the boundary, the limit, the furthest back in time we can ever look with light. And yet, here it is, still traveling, still reaching us, still carrying information from an era so distant that it's hard to even comprehend. Every time we study the CMB, we're looking directly at the universe's infancy. We're seeing the conditions that existed when the cosmos was less than 400,000 years old, when there were no stars, no galaxies, no complexity, just the simplest elements and the seeds of everything to come. Think about the journey this light has taken. It was released nearly 14 billion years ago in every direction at once. It traveled through expanding space, through voids and clusters of galaxies, through regions where stars were born and died, where planets formed, where life eventually emerged, and it reached us. Here, now there's something poetic about that. This ancient light, stretched and cooled but never destroyed, has been traveling across the universe for longer than Earth has existed, longer than the sun has been shining, longer than our galaxy has had its current shape. It crossed unimaginable distances just to arrive at this moment, where we have the technology and the curiosity to detect it and understand what it means. The oldest light in the universe isn't gone. It's not lost in some unreachable corner of space. It's everywhere, surrounding us, passing through us, hiding in plain sight, waiting for us to look up and understand what it's telling us about where we came from, what the universe is made of, and where we're all going. So there you have it. The universe's first light didn't disappear. It survived. It stretched with the expanding cosmos, cooled from a brilliant glow into faint microwaves, and now it surrounds us constantly, a permanent reminder of the Big Bang itself. If this topic fascinated you, there's so much more to explore about the early universe, cosmology, and the incredible tools we use to study it all. I encourage you to keep learning. Check out the ebook in the description if you want to go deeper into the science behind the cosmic microwave background, and stay curious, because the universe has more secrets to reveal, and we're only just beginning to understand them. Thanks for watching.